All right, let's talk about chips. You know, the Android operating system is undoubtedly the single most disruptive force in computing in the last 20 years. Whether you're a large company in any industry or a small startup trying to build any new gadget, the Android operating system is the most accessible and the most capable operating system you can get your hands on. It's open source. No wonder the computing revolution in China took off on the backs of the Android operating system and is now the fastest growing mobile computing market in the world. Android started out in the phone industry, completely disrupted the phone market. Then it worked its way into tablets. But that's not where it's going to end. Because it's an operating system that's free to all. Because it's an operating system that allows every company, every country, every industry to freely innovate. And because it is a virtually complete operating system, by virtue of the fact that so many of us make contributions to it. There are more engineers working on Android. There are more engineers working around the world in the Android ecosystem than any ecosystem today. And so it stands to reason that the positive feedback system is going to fuel its disruption. At this point, it's kind of hard to imagine stopping it. But it's wonderful for the world. When we think about building Tegra, our mobile processor, we think about what we can do to take the Android operating system, in combination, take it into new markets. Markets where our expertise can especially serve. Markets where visual computing matters. We started out by building the Tegra 2, the world's first dual-core processor. At the time, people asked us, why would you need a dual-core processor? Then we took that to Tegra 3, the world's first quad-core processor. People asked us why we needed a quad-core processor. And it's all very clear now that in a mobile environment, in a mobile context, there are more and more activities that are happening simultaneously. So the question is, where do we go from here? Now there's some new industries that I think Android will continue to advance into and make a contribution to. One of them, of course, is television. That one's a foregone conclusion. It's not if, it's simply when. 4K televisions are coming, smart televisions are coming. It stands to reason that Android is going to be a very important factor in that. Consoles. We happen to believe that the Android operating system is going to be the most important platform for game consoles in the future. And the reason for that is because you have all of your digital asset in Android. Why would you want to be home, connected to television, and then have access to all of your photographs or all of your music, of all of your movies, and all of your video games? It's simply a matter of time. It's simply a matter of time before Android also disrupts the video game console industry. It is the reason why we built Shield, so that we can engage it and start to make a contribution to it. We also believe that Android would make a difference in the car industry. The car industry is one of the most exciting industries in the world for many of us because we love cars, but there's a second reason. We happen to believe that the car will be your most important mobile computer. It is likely to be our most personal robot someday. It is already our most expensive consumer electronics owning, and it stands to reason that it's also going to be the most advanced. Now, it happens to have some of the most pioneering minds and some of the brightest engineers working in that industry, because they also love cars. And so I think this is an area that's going to make huge contributions, and I'll come back to that in just a moment. And so the question then, after Tegra 2, the world's first dual core, after Tegra 3, the world's first quad core, and then we double the performance of that with Tegra 4, what's next for us? What's next for us? I mean, what could we possibly do? I guess we could do 8 cores, but that seems pretty pedestrian. That seems pretty obvious. We could do 12 cores, that's more than 8. However, I think that maybe we could do better than that. What we decided to do was we decided to make Tegra K1 the world's first 192 core processor. 192 CUDA cores, all programmable by programs, all fully programmable, all massively parallel. And this is the first GPU. The reason why we decided to call it Tegra K1 is because this is the first GPU that took a vast jump from the previous generation. It's almost inappropriate to call it Tegra 5 because it's simply not linear. We decided to call it Tegra K1. We decided to call it Tegra K1 because it's based on the Kepler architecture. As many of you know, Kepler is the most successful GPU architecture that we have ever created, and it's the most important GPU architecture the industry had ever known. This architecture, because it is so energy efficient, has made it possible, and so programmable, has made it possible for us to extend the GPU from not just desktop computers to workstations, but all the way into the cloud with Grid, and into supercomputers with Tesla. One singular architecture, all compatible, is now able to span computing from a few watts all the way to megawatts, from 192 cores all the way to 36 million cores running our nation's fastest supercomputer, all based on the exact same architecture called Kepler. So we're really, really excited today that with Tegra, we've bridged the gap. We've brought mobile computing to the same level as desktop computing. We've brought mobile computing to the same level as supercomputing. We've brought the heart of GeForce and the soul of Tesla to the Tegra family. We've brought the heart of GeForce and the soul of Tesla to mobile computing, and we're really excited about that. Now, what's the benefit? What's the benefit of that? Well, the first benefit is solving, in fact, a very significant problem for game developers. If you take a look at game development today, just as you saw with Batman, the production value is incredible. It's completely cinematic. It's cinematic and also interactive at the same time. The computer graphics is cinematic. The experience is cinematic. The story has to be sufficiently broad and large and large in scope that you can actually enjoy the video game for 8 hours at a time, 10 hours at a time, 20 hours at a time. So there's enormous depth to the video games. And it stands to reason, with so much artistic contribution and so much technical contribution, that the production value, the production cost would be so high. In fact, most AAA titles today cost more than $100 million. Now, there's only one thing that you can do to solve that problem. You can either reduce the production value, or you have to have a larger footprint. You have to find a way, as a game developer, to reach more users. Well, in order to reach more users, unfortunately, the architectures are radically different. When you take a look at each one of the game platforms, the architectures historically were very different. They're becoming more and more similar. However, the architecture of mobile devices, which is the largest computing platform in the world today, and the architecture of next generation game consoles are radically different. One of them is based on OpenGL ES 3.0, and the other one is based on OpenGL 4.3. The capabilities are radically different. The capabilities, the features. And so, for a game developer, the diversity of the platforms creates another degree of complexity that is simply intolerable. The developer's dilemma. They want to build great games, they want to take the financial risk, but they need to have large enough footprint that can accept and help people enjoy the creation that they make. And so today, we're incredibly excited to announce that Epic Games is going to bring their next generation engine, the Unreal Engine 4, to the Tegra K1. And Tim is a man of few words, for all of you guys who know Tim. And he has the highest expectations. We've been working with Tim now for 20 years. He has the highest expectations of anybody in the game industry. And he says this so cleanly. He says we can take absolutely anything that runs on PC or high-end console and run it on Tegra now. I didn't think that we'd be at this level on mobile for another 3 to 4 years. Now let's take a look at what he meant by that. So if you look at this is Unreal Engine 3. This is the last generation game console. In the year 2002, we launched MV30, which was GeForce effects, with the invention of DX9. DX9 brought to the world programmable shading. And the effect that we saw in video games were per pixel lighting. So video games became bumpy and shiny. Okay, whereas before it looked chalky and flat, now it looks bumpy and shiny. It came to life. And modern video games are still based on DX9. It wasn't for several years later that Xbox 360 and PlayStation 3 brought DX9 to game consoles. And then many years after that, it came to mobile devices. For the very first time, with Unreal Engine 3, with Infinity Blade from Epic running on an iPad. iPad was the first capable machine to be able to run an engine that was introduced in the year 2002. A span of 8 years' time. A span of 8 years' time that it took for the Unreal 3 engine that runs on Xbox 360 and the PlayStation 3 to finally be able to run on a mobile device. Well, that entire 8 years is what we consider last generation. It was the DX9 era. The DX9 era. If you take a look at most video games today, with the exception of some of the more modern video games that we're showing you, when you take a look at a mobile device or you look at a video game today, it's mostly DX9. That's the look of DX9. Well, here is the beginning of next generation. Next generation started with DX 11.1. I'll show you what DX 11.1 can do in just a second. We introduced it with Kepler. 1 year later, because of this incredible imperative to unify the platforms for the video game industry, the new game consoles are effectively PCs. It's architecturally identical to a PC. It's because of this incredible imperative to keep the platforms the same. 1 year later, the game console industry brought the same architecture to game consoles. As a result, now the game developers have a reasonable footprint to target with next generation DX11 games running Unreal Engine 4. But here's the really exciting thing for Tim. And what he said earlier is this. This time around, because of what we've done with Tegra K1, we have now reduced the amount of time that it's taken for next generation platforms to be able to reach not just PCs, not just consoles, but also mobile devices of all kinds. The benefits to game developers is really immense. Literally one singular architecture, one singular platform, and more importantly, one engine. Now the Unreal Engine, many of you guys have known, is is, I've been tracking the video game industry, is the most successful game engine of all time. Unreal Engine is effectively the operating system of games. The game AI, the game physics, the game rendering engine, it basically embodies the runtime of modern video games. Unreal Engine 3 had hundreds of games that were credited to it. And here comes Unreal Engine 4, the next generation. So that's what Tim is really excited about. Now when you take a look at Unreal Engine 3 and you compare that to Unreal Engine 4, it's really incomparable. Because Unreal Engine 4 is all about being photoreal. This relentless pursuit for photorealism. Several factors, several characteristics make the next generation game content look so distinguished relative to the previous generation. The first thing that you'll see is that all of the rendering is physically based, meaning that we're capturing the microstructures of the materials and how it responds to light physics. And so as a result, you could almost feel the material physics, the material properties of everything in the scene. The second thing is the advanced lighting systems. It's no longer just the unidirectional light. Light is coming from all over. It's as close to global illumination as we've ever come in real time. It also includes physics simulations so that the world comes to life. And to make it all possible requires this new technology called multiple render targets. Really rendering simultaneously into a whole lot of different buffers at the same time, and then doing screen space computations to resolve the final scene. The result is a photorealistic and a stunning looking image. Next generation gaming is really going to be a big deal. This is the kind of imagery we like to create on Tegra. And so let's show you what that means. Now, very few people, very few computer graphics companies would ever lead with a human face as a demonstration. And the reason for that is because the human face is so hard. We know what a human face looks like. Now, if I were to put a monster up here, everybody would say, wow, that's a good looking monster. And because we've never seen a monster before. So long as it's bright and shiny, it looks really upset, I think everybody would be rather satisfied by it. Well, this particular face is being rendered in real time, and it's not a photograph. Lucas, let's show them what Ari can do. Now, let me explain some of the technology behind it. So first of all, in order to capture the human face, our skin is a living thing. Light penetrates through our outer layers, goes into the skin, bounces around inside, and then scatters, and then comes out, picking up some of the tone of the color of your blood. And as a result, when you look at it, it looks alive. Of course, there's a lot of pores. Your eyes are the windows to the soul. And so obviously the eyes have to look alive. In this particular case, we use a technology called ray tracing to ray trace the eyes. That's why the eye crystal looks like it's alive. And of course, all of the shadows are being rendered so beautifully. You see no triangles, no faceting whatsoever. Triangles have disappeared. The lighting system is so sophisticated we can pick up the little sheen of the oil of his face. Now let's change, I love the soft shadows underneath the lips. I mean, it's so exquisitely rendered. Photorealistic. Okay, let's Lucas, walk us through some of this stuff. You do some talking here. Let me spare a few seconds.
Sure. So yeah, this is digital IRA, and it's a data set from our friends at USC. And if you guys have been watching previous time, we've actually seen that we've shown it on a GTX Titan, the same data set. So it's pretty cool this works on a K1. Yeah, and as Jensen said, there's subsurface scattering in the the light going through the ears. Also, the light from as the shadow lands behind his nose. You can see if you turn it off, you can just see that like his skin just kind of looks like plaster or something. It doesn't have the right effect. And so that's something that's it's quite computationally expensive and something that using Tegra K1 is possible on mobile finally.
Now change the lighting environment. This isn't just lighting, this is image-based lighting. And look how the light is coming shining through his ears. You get some rim lighting off the edge of his head. And let's change the lighting yet again. That's just really stunning. If he was just more attractive. I could sit here and look at him all night. Okay, so this is a face only a mother or a computer graphics company could love. Ira is actually his real name. He's a very good friend, and I apologize for that funny comment. Okay, but show us now what it's like if we didn't have all of the photoreal capabilities that Tegra offers, Tegra K1 offers.
Sure.
So this is what a face would look like using today's computer graphics. And notice it's a convincing head. I mean, when you look at it, you go, that's a head. There's no question that's human, but there's no question also it's computer graphics. And this is basically OpenGL ES 3.0. Okay? All right, that's fantastic. Let's show them something else. Let's show them something else. All right, so this is, we want to do something that is a big world, and this is something that Lucas did. Lucas, why don't you talk us through it, and I'll ask you some questions along the way.
Sure. So yeah, it's a big superstructure actually, as opposed to just a head, and it has a lot of interesting features that are cool. We have pretty rich metallic materials. We have HDR lighting and tone mapping, cinematic effects with lens flare and bloom.
Now show them what global illumination and HDR means.
Sure.
Can you do that?
Yeah.
So do you guys know what HDR means? High dynamic range. Your eyes could see much larger dynamic range than a computer monitor 16 bits per pixel can render. Okay? And so the way that we solve this problem, is we render to a much larger dynamic range inside the graphics processor. Okay? Then we do essentially a tone map, a histogram of all of the tones in the scene. Now we figure out where the tones are, and we remap that tone into a smaller color space. And as a result, we retain the large distributions of the large contrasts. The deep darks and the bright whites are retained, but we remap, if you will, the rest of the dynamic range to fit back into that of a computer monitor.
And you can see that as you go down, so like behind this building, as you see that it's pretty dark, right? But then as you zoom in and you cover up, the sky, which is very bright, you start to see more detail that's in the previous dark area, like when your eyes adapt, to the brightness of the scene. But then as you go up and you expose more of the sun, you'll see that it also, it adjusts to allow you to see the sky, which, relative to the back of the building is very bright. Yeah.
Did you show us what global illumination and HDR turned off would look like?
Yeah, definitely. So sort of rendering this with what it looks like using OpenGL ES3.
So this looks like a computer graphics game today?
Yeah, I mean...
Right?
Yeah.
Not with this many geometry. I mean, this is still rich with polygons, but without global illumination, without high dynamic range, this is what your games would look like. And let's turn it back on. It's almost unbearable to watch. Okay, so that's special effects, but the world is not always so peaceful, right? I mean, sometimes there's astronomical events.
That's true.
I mean, you know what? S could happen, right?
Yeah.
Oh my goodness.
So we have a pretty cool bullet time effect here where you can sort of pan around and see all the volumetric explosions, particles, debris. We're using compute shaders to compute the movement of things and the particle effects that happen.
So what's happening here is that Lucas is using the Tegra K1's 192 parallel cores to do physics processing. This is the same physics processing that supercomputers use for fluid dynamics, for nanomolecular dynamics, particle simulations for astrophysics. It's exactly the same architecture, exactly the same type of program. Now it's running on 192 cores on the Tegra K1. Okay, all right. You can play it by yourself on the side there. Let's keep moving. Okay, so that's I think Lucas calls that demo the Meteor. All right, give him a round of applause. Global illumination, high dynamic range, incredible amounts of geometry, and now physics processing, all being done on the Tegra K1. Now, I want to show you a few more examples of the power of next generation graphics. This is what a state-of-the-art mobile application, mobile game looks today. In fact, this is a game that's featured on Tegra 4, and it's on Tegra Zone. It's a fantastic game, and they're doing incredibly well. However, this is what last generation graphics looks like. Let's show them what next generation graphics look like. Now let's just kind of take this in a little bit. This particular image, notice the trash can? You see no triangles whatsoever. All the faceting is gone. The detail is so exquisite that when the light shines on it, it looks perfectly smooth. All the shadows are soft. It seems like light is coming from all over. It's being lit. The scene is being lit in darkness. There isn't one particular light that's showing up somewhere, but light is bouncing all over the walls using this technology called global illumination, where everything in the scene is a light source. Everything in the scene is a light source, and it helps create the subtle mood that you see in these dark environments. Notice the volumetric fog that's starting to roll in. And just the texture quality is just so incredible. But, you know, this looks like a photograph. Andrew, why don't you take us around here?
Sure thing, Jensen.
Why don't you take us around and talk us about some of this?
Okay, so this, you mentioned before Unreal 4. This is Unreal 4 running on Tegra K1. So this is a demo.
Ladies and gentlemen, this is Unreal Engine 4 running on Tegra K1.
Yeah, so this is a wonderful demo that Epic put together to show off some of the features of their engine. As you mentioned, the art quality is second to none. The textures are amazing, and also lots of little effects. As we go around, I'll point some of them out.
Look at the water dripping off the wall.
Yeah, up here.
The lens flare. You look at the sun, high dynamic range. Look how bright the brights are and how dark the darks are. Okay, imagine a camera doing this. Really hard time with a camera doing this. Now it's computer graphics doing this.
So as you mentioned before, this is trying to simulate exactly what your eye sees. And indeed, they have a feature called pupil adaptation, where they calculate the luminance in the scene. And just like you would if you went from a bright environment into a dark environment, if you were outside and ran into a room, your pupil takes a little while to sort of adapt to that. They've built that into this engine as well. It gives wonderful effects. They've got lots of nice reflective surfaces as well. So over here we have like a mirror, we have tiles, the trash can over here is reflecting the rest of the room.
Now that trash can obviously looks so real because it's somehow simulated in a physically based ways. So that when light bounces off of it, you could almost feel the steel that it's made of.
Absolutely, and you can see the water dripping down in the back there. And as we come along here, there's a more sort of plastic posters, reflections again off the tiles. The quality of the textures is unbelievable.
This is real-time computer graphics, ladies and gentlemen, on a little mobile chip.
Yeah, it's tiny. And you mentioned before bumpy shiny, you always have to have something shiny. So this is a nice shiny pipe, whereas everything else in the scene is quite rusty, and somehow this has managed to stay shiny. The final feature I'll mention just briefly, you see here there's a light sparking. And they do some very clever things with particle effects, and they actually put physics on the particle effects so that the sparks don't just fly through the wall and through all the objects in the scene. They actually bounce off the wall, and then you can see them pull.
And they're actually lighting the environment.
And they are lighting, yeah. So there's
Right.
a light kicking out, and also the effects come down and then bounce around a little bit, give a nice.
So they all become light sources, and they cast shadows, and you can just see it. It's fantastic. It's just absolutely exquisite. Now, these little tiny details is what increases the production value of games. And we see this with movies today. There are so many things that they do, the attention to detail, that they obviously don't have to do. They obviously don't have to do. But they do it because they want to create something that is exquisite. And you can just tell now, the engine makes it possible for them to do that. Okay, that's fantastic. Let's take a look at a couple things. This is another scene of the state-of-the-art in mobile graphics today. And in fact, I think this is a game on iOS. What we want to do is we want to show you, you could just tell this is a cartoon. It's lifeless, it's kind of dead. You recognize the objects, but for some reason it just doesn't tell you that it's alive. Now, what is the missing part that goes from this to reality? One of them, of course, is the way that the lighting behaves. We know that light doesn't work like this, that there are just subtle shadows and the reflections and the way that light is occluded in the corners, and you know, those type of effects our eyes are looking for, and when we don't see it, we know that it's not real. And so let's take it to the next demo. This is also running on Unreal Engine 4, and here we'd like to show you a couple of things. This is not a photograph.
This is not a photo.
This is not a photograph. We're in Vegas, so this is Frank Sinatra music. Okay. Now you can almost feel this room coming alive. Now what you're looking at is two very important technologies. One of them is physically based rendering. Now, if that couch doesn't look soft, it almost looks like you could sit on it. I could almost imagine finding some quarters underneath it. Look how beautiful that is. The lighting of it is just incredibly exquisite. And then we're going to show you the second technology is global illumination. If you look at all the lighting around, everything is a light source. So light is bouncing around the environment, and as a result, it's casting more than one shadow, and you're seeing soft shadows everywhere. And look at that wood floor. Wow. Does that look like wood floor? Unreal Engine 4 running on Tegra K1. That's fantastic. Good job, man. Okay, so now let's take a look at all this stuff in a game. Okay, so this is an Unreal Engine game. This is Trine 2. This runs on a high-end PC today. It runs on a high-end game console today. And look, well, Andrew, you're the master of this game. Tell us about it.
Hello again. So this is by a company called Frozen Byte. It's a custom game they've made. This is the first for mobile. It's a really fun game. It's kind of like a platformer, 2.5D. But the cool thing is you have 3 characters. So you can have your warrior guy. You can switch to have a wizard, and he can like.
Now remember, this is a mobile device that's been blown up to the size of a theater. Okay?
Absolutely.
This is a mobile device that's been blown up to the size of a theater. Look at the exquisite detail.
They've used Nvidia physics actually in this. So you interact, and a lot of the puzzles are based on physics, and you have to sort of figure out different ways. And we'll see that just up here. So if I run inside now, past the beautiful sort of Egyptian statues. So here we have a puzzle. This one's fairly straightforward, and I have played it a couple times. So you can choose which character you want. So I can try and reflect this beam. And you note the way the lighting follows the beam around. Yeah.
Oh, that's hot.
Yeah. So I think I'm actually going to use the wizard here, and I'm going to grab this box and hit the special key, and I should be able to open the door. There we go.
Now, while he's doing that, look at how the lighting is changing the environment. Everything's all lit so beautifully.
Yeah,
It's all dynamic lighting.
It's a beautiful game. The artwork in this is just exquisite. Ow.
Now, please hurry. Please hurry.
Please. Oh, hang on.
Don't die. Don't die.
Okay. Oh, hang on.
Whoa!
There we go. Okay.
Now, all of this behavior is happening with physics simulation. So you can just see how heavy that rock was. You can feel it.
So now we're down in a crypt.
Who's this here?
Goblins seem to
Uh-oh.
have taken a fancy to it.
Some kind of goblin?
Here
Could be.
comes a bad guy. And there we go.
Okay, fantastic. Good job. Okay, so Tegra K1, Unreal Engine 4, next generation graphics on a mobile device for the very first time. Next generation graphics, physically based rendering, advanced lighting systems to create effects like global illumination, particle systems and physics simulation, amazing visual effects. Now, if you compare Tegra K1 to a couple of other well-known platforms in the world, one of them is the PlayStation 3 and one of them is the Xbox 360. Both of them are last generation graphics capabilities called DX9. Tegra K1 is based on DX11. But if you look at the horsepower, just the raw horsepower alone, the GPU has more horsepower than both Xbox 360 and PlayStation 3, and the CPU is far and away more powerful than both the Xbox 360 and the PlayStation 3. And all of that is made possible because of mobile technology now available in just a few watts. And so what you're going to have is essentially the visual richness of next generation capability, but the horsepower of a game console right in your palms. Really, really amazing. So I'm super excited to introduce Tegra K1 to you. Now, if you were to compare Tegra K1 to another platform, this is the most advanced processor on the market today, the highest end tablet from Apple, Apple's with Apple A7. And if you compare TK1, Tegra K1, to Apple's A7, is almost 3 times the performance on just a benchmark that runs using yesterday's graphics technology, OpenGL ES 3.0. Okay, this is using old, last generation computer graphics technology. We're already miles ahead. But when you consider it next generation graphics capability, we're just so far ahead at this point, and that's the reason why Tim Sweeney is as excited as he is. Tegra K1. Well, there's a lot of things that I can tell you about Tegra K1. There's a lot of features I'd love to show you. I urge you to take a look at the demos that we have set up for you. The 4K demos, the UI, really, really beautiful. When you take a look at all of our camera applications and camera capability, super exciting. The performance is wonderful. So there's a lot of things I can go over with you, but I really would like to focus on one surprise. Tegra K1 is the world's first 192 core processor. But I have one surprise for you. Tegra K1 comes in 2 versions. The first version, one version is the quad-core A15, but another version is based on our Denver CPU. I've been talking to you about Denver for some time. This is an endeavor that we've taken some time to do. It's a full custom CPU. It is based on ARM's V8 64-bit. And it's designed to be very high performance single-threaded and very high performance multi-threaded processor. And I'm delighted to announce today that Tegra K1 will also come with dual-core Denver. Now, I know what you're thinking. I know what you're thinking. This is probably a PowerPoint launch. Right? Right, okay. Well, I'm happy to say that Tegra K1 with dual-core Denver has been back for a few days. It's been back for a few days, and I know how excited everybody is about Denver, and so I thought, you know, what the heck? Let's give it a try. And ladies and gentlemen, this baby's only been back a few days, okay? And if she falls on her face, trips up while she's introducing herself to you, let's all cut her some slack. She's only been out a few days, okay? So ladies and gentlemen, Tegra K1 with Denver. Now, what you're looking at is the Android operating system running on Tegra K1. And Lazar, why don't you take it out for a spin?
Sure.
Wow, look at that. It's only the, I know. That's this. Look, the applause comes from only geeks. Everybody else in the room's going, I've seen a desktop. You know? Well, look. When you work on a chip for 5 years, and it comes back and it's not a brick, you're just so happy. I am so happy. So Denver is a full custom CPU. It's going to be incredibly fast, and this is the world's first demonstration of 64-bit V8 ARM on Android. And so let's prove it to them. Wow, that is really sexy, guys. There you have it, ladies and gentlemen. Tegra K1 with dual-core Denver 64-bit ARM CPU. All right. Well, let's not push this baby too far. Okay, let's not push this baby too far because we have a few more demonstrations to give you, and I don't have very much more time. So thank you very much, Lazar. Good job. So there you have it, Tegra K1, the world's first 192-core super chip. It's one chip with two versions, quad-core A15, dual Denver CPUs. A15 is obviously 32 bits, Denver is 64 bits. A15 is 3-way superscalar. Denver is 7-way superscalar. It runs up to 2.5 gigahertz, and it's got a pretty healthy cache, 128 kilobytes and 64 kilobytes of I and D L1 cache. Okay, ladies and gentlemen, Tegra K1. Now I want to talk about cars. I've got a few more surprises for you. Tegra K1's got a few more things up its sleeves. Don't forget the heritage of this processor. First of all, we've had a love affair with the automotive industry for 2 decades. Our engagement with the automotive industry started with design, and we eventually moved into styling as we introduced computational rendering. We then moved into simulation and engineering when we introduced GPU computing with Tesla. So now it can be used in fluid dynamics and crash simulations. And as we improve the visual quality of rendering to the point where it's nearly photorealistic, we are now able to use our technology for marketing and sales as well. You're going to see some really exciting innovations in this area, using the original data of the car design for marketing, for sales, for even point of sales. We've also, with the help and the tutoring and the mentoring of some wonderful customers, introduced us to in-car electronics. And over the last several years, we've learned so much about this field. We came into it because we felt that the car was going to become one of the richest areas where we can make a contribution with visual computing. What you see when you're driving, what you experience when you're driving, the industrial design of the car matters so much. But because we also know that GPU computing was going to be used in such exciting ways that we believe that parallel computing was going to revolutionize the way that a car is built altogether. We're working in multiple areas now in the car. All the way from the beginning of styling and design, all the way into the car, from how it looks to how it drives. But let me show you a few things first. When you come to an Nvidia conference, you always have to see beautiful graphics. And so let me just show you now what state-of-the-art, physically based computer graphics looks like. Now what I'm standing in front of is not a photograph, it is real time. So let's, Sean, why don't we take it for a spin, and why don't you twirl it around just one time, and then, okay, so let me just show you, let me just explain to you what just happened. In that moment, when Sean changed the view of this car in real time, a supercomputer in Santa Clara simulated the light rays of a few billion rays, bounced all around this environment, through the glass, reflected off the glass, refracted off the glass, through other glass, bounced off the upholstery inside, comes back out, goes through the headlights, the multiple layers of crystals inside the headlights, bounces all around, and eventually enters your eyes. This light simulation, interacting with physically accurate materials. The car paint is physically modeled, and that's why you could almost feel like you could touch it. Okay? All of this stuff is simulated in a supercomputer in Santa Clara. So of course, you could imagine a retail shop being able to configure your own car and design it on a tablet and simulate it and render it exactly as it will look for your customers. Why don't we spin around a couple more times? Look at the headlights. Now, what you're seeing in the sparkles is ultimately that pixel hasn't been resolved yet. We're still waiting to accumulate all the light rays that are bouncing all over that environment. And as you sit here and just kind of look around, you realize as you're looking around, it's resolving this image in real time. The world's first real-time interactive ray tracing engine that's physically accurate. It looks like it's sitting right in front of you. Okay, let's take a look at one more view. Now let's help me. Let's go back and configure it a bit. Okay, so what you were looking at is actually a tool and has these materials that you can select. So you like white. How about let's just pick one other. Orange? Nah, come on. Something aggressive. Something that Justin Bieber would like. Like, say, chrome. Let's make one for Justin. There you go. The world's first chrome car. Pretty fantastic. And it's physically modeled, so it looks so real. It looks just so real. Okay, good job. Thank you very much. So this is how Nvidia's technology is used in design and styling. Now, we've been in the car industry for a long time. Almost every single car that you see on the road is designed with our technology at some point. But we're also inside about 4.5 million cars now. And we're designed into some 20 more brands with 100 more models coming. Millions more cars will come with Nvidia technology inside. We're just incredibly excited by the cool cars that we're in. The Audi A3 is just a revolutionary car. If you ever get a chance to drive that, I'd really urge you to take a look at that. And of course, the new BMW i3 and i8, and the Tesla model, the Tesla sedan, and also the Tesla crossover that's coming out, Model X. Okay, so lots of cars. Well, today we'd like to introduce you, of course, to the Tegra K1 VCM. The Tegra K1 VCM is really about bringing supercomputing into your car. And it was really interesting, we were describing this to one of the reviewers of Car and Driver, and he literally just said himself that this is next generation Tegra will perform at this level with 384 gigaflops with 4 processors per car. A 2-car garage would have as much computing power as a $120 million Blue Mountain supercomputer. So he quickly equated it to a supercomputer. And in fact, just as Tegra K1 has the heart of GeForce, it does have the soul of Tesla. It is the identical same architecture. This architecture powers the world's 10 of the top 10 greenest supercomputers. Every single energy efficient supercomputer in the world today, in the top 10 list, are powered by the Kepler architecture. That same architecture is now in Tegra K1. The question is, what do we want to do with it? I want to show you 2 things. I want to show you 2 reasons why we need a supercomputer in future cars. The first reason, of course, is advanced driver assistance. This is an area that has incredible focus today. It's incredibly exciting because this is the path that leads to the semi-autonomous cars. This is also exciting because it's going to bring magic to the car industry. Your car is going to do things that most people won't be able to understand. And they won't be able to understand it because we have a supercomputer in the car doing amazing things. Using image processing, computer vision, artificial intelligence, and all of the technologies that we've invested over the years, it is now possible with a rich number of sensors around the car to do magical things. Magical things. Now, these magical things start with basic things. The thing that we're going to do today is we're going to make possible a programmable platform, the first time ever, a programmable platform for ADAS, for advanced driver assistance. Today, most ADAS systems are fixed function boxes that are inside the car. But we know that computer vision, deep learning, machine learning, these fields are advancing at amazing rates. We need to provide platforms that when the car is connected, could afford us to download new algorithms that makes the car better and smarter all the time. So that your car becomes better every day and it doesn't stay static from the time that you buy it. And so Tegra K1 is a programmable platform that makes it possible for us to run the types of applications that these dedicated ADAS boxes do today. Now that the platform exists and allows computer architects and algorithm developers to develop these algorithms, you're going to see the rapid rate of algorithm enhancement. What starts out as detecting a feature, which is a car in front of you, collision avoidance, slowing you down, recognizing lanes, keeping you inside the lane. These features will quickly evolve to the point where your car finds its way eventually to becoming an autopilot. We're super excited about this new capability. It brings to bear our last decade of work in the area of computer vision, in GPU computing, and all the work that we've been doing in this area, we can now bring to bear for the very first time in mobile devices. So Tegra K1 for ADAS. The second thing I want to show you has to do with graphics, of course. As you know, we care a lot about photorealistic graphics. And we see no reason why industrial design should end at the physical construction of the car. Industrial design should extend all the way into all of the digital electronics. What you're looking at here are not pictures. These are real-time computer-generated images, using exactly the same algorithms in the same system that was used when we showed you the car just now. Now, you're looking at chrome, you're looking at jade, you're looking at plastic, you're looking at crystal, you're looking at gold, copper, you've got ceramic, you have rubber way on the end, you have marble. You can just see what the materials are. And the light is bouncing off of it in such a realistic way because everything has been physically modeled. Let's just change a couple of things real quick and show people what's possible. I love the fact that Sean, if you rotate a little bit so that we can see through the crystals. I love the crystal. You're seeing reflections through everything, of course. Are you going to change something? Okay, one more and then we're... Were you going to do something, Sean?
Yeah, I've changed a couple.
Well, you did?
What else would you like to see?
Oh, no, this is fine. This is fine. I was just trying to keep up with you. I was trying to figure out what you were going to do. Okay, so this is using physically based computer graphics so that we can simulate and render photorealistic objects and so that we can extend this capability into the car. So today I want to show you a brand new technology for Tegra K1 VCM that we'd like to bring to the automotive industry. It's called Project Mercury. Project Mercury is intended to make a configurable, customizable, and a photorealistic environment for industrial designers to extend their industrial design artistry into the digital dashboard. Okay, computer graphics is going to be like you've never seen before. And so over here, let's come over here, and Justin, why don't you tell us what you got?
Hey Jensen, I'm thrilled to help present Project Mercury because this is a year-long labor of love by our team, and it really represents the first time we're bringing physically accurate gauges, automotive gauges, into the car. So the reason we're showing all of these parts here instead of presenting it all neat and tidy up on the screen is because we want you to understand that this is very real and there's different physical pieces here. So if you look at this piece right here, this is our K1 automotive development environment. And this up here is an automotive grade high definition display that would go behind the steering wheel for the instrument clusters themselves. And so these two parts would actually go into a car. This represents a K1 tablet that you might have at home or at a showroom that would let you configure. So you can see it's actually running Android, which is totally different than something that would be behind the steering wheel for gauges themselves. So let's start by looking at this part that would be in the car, because this is ultimately what's the most thrilling part of this. So as we zoom in on it, you can start to see the detail of the materials. And as you were talking about, Jensen, we've been using physically accurate materials to render designs for the exterior of vehicles for a long time. So what we're doing here is we're taking those exact same materials called MDL and we're putting them inside the car. So you can see up here brushed nickel. This is like a powder coat here, shiny titanium. It's very highly detailed, and I welcome you to come to the demo room and get a very much closer look.
Well, let's configure something.
Okay.
Let's make something for ourselves.
Okay. So right before I'm going to drop down and configure it, I just want to point out that we've got film quality details to this. We realize that something to look realistic has to be nearly perfect. So we can see this is all 3D, depth of field, refraction on the glass, illumination from the environment. We can change the environment and create warm glowing lights that you might see inside of the car. So dropping down to this configuration that you might have inside of your room, living room, or maybe at a showroom as you purchase a car, you can see we have the gauge right here in this location here. And there's different parts to it. You can see the powder coat is selected and the outer ring is selected right here. So if I wanted to change that a little bit, perhaps I could change that outer ring to like a shiny titanium. You can look at the sample material here, and we can change it. Maybe we want a highly brushed and soft effect, or maybe we want it highly reflective. Going back over here, we can check out other types of materials. This is a smooth rubber. Maybe we'd like it to be highly bumpy. I can zoom in on this a little bit tighter and get a good look at this bumpy white rubber that we're using. Another part of the gauge here is this accent color. And so I can click on that and see that it's brushed nickel. I could, for example, change the color of it to red or blue, or maybe just pick something else entirely. Moving past titanium, powder coat, maybe red. And powder coat's very diffuse, it's not reflective at all, so it's very pretty right there. So the last thing I'll change.
Justin, this is just our design. This is a platform called UI Composer for designing this digital dash system. And a car company could import their own design of a digital dash and whatever wild and crazy and really beautiful designs that they can import. That comes into the UI Composer, and then we can help them, as a result, turn it into a running digital dashboard.
Yeah, and so these materials are our materials, but let's say an automotive company had their car paint, their fabrics, their leather, things like that. They could scan and import those directly into here and use those as they are. So if we want to just finish things up, we can go back up here and see what we've created in the environment. And maybe I'll turn off the background so that it looks like it would actually be inside of the vehicle, and switch through a few different sets. We can see that we've got a wide variety of different capabilities here. And maybe we finish on this, and you can sort of compare. What's interesting is we've got kind of a scratched up metal here, scuffs on here, and we can compare the real physical metal we have here with what's being presented inside of these gauges. You can see the reflections are similar, and we really believe that this is something physically accurate. And this is a glimpse of the future. We aim for perfection. We see areas we can continue to improve always, because that's what we do. But
That's really cool.
I think this is going to be exciting.
That's terrific. I think I just lost my voice.
Do you want me to wrap up?
All right, no. Good job. Good job, Justin. Wow. I was so impressed it took my breath away. Congratulate the team. This has been a year's endeavor. We gave Justin and the team the dream of bringing photorealistic rendering to cars, something that we do in supercomputers in the cloud. We wanted to be able to use exactly the same material library. It's called MDL. That same material library that car companies use to drive the styling of their cars and the rendering of their cars. Want to be able to use that same exact library in a real-time way in this mobile processor we call the Tegra K1. And they've been working their butts off. I'm just so pleased with the results. This is really groundbreaking work. So ladies and gentlemen, there you have it. That's Tegra K1. I do have one more surprise. Maybe this is more of a confession. It's not quite a surprise, this is more of a confession. So Tegra K1 is probably the most ambitious project that we have ever worked on. It is the culmination of many years of work in the GPU industry, taking the same architecture that is the heart of GeForce, the soul of Tesla, the same architecture that runs and powers the nation, our nation and the world's supercomputers, and to bring it into a mobile form factor so that we can revolutionize mobile computing. The two very important areas that we wanted to revolutionize was bringing next generation games to mobile form factors. It could be a mobile device like a phone, it could be a tablet, it could be a game console that utilizes mobile technology. The second area was automotive. We believe that such a supercomputing technology inside your car could help revolutionize the car and can make possible next generation cars to come more quickly. And so I told the guys, look, Tegra K1 is impossibly advanced. It's impossibly advanced. It's like out of this world. It's practically built by aliens. And the engineers have worked so hard on this for so many years. I want you guys to go out and launch this product and put a marketing campaign behind it that is of equal, that rivals the technical contributions. I want you guys to go do something that when we sit back, will have global reach. And people will think that, my God, everybody knows about it. And by the way, you have no marketing budget. And so, ladies and gentlemen, it is true. The Nvidia marketing team is behind this phenomenon. What you're looking at here is 310 feet in diameter. It is what people call a crop circle. This is a field of barley. I told them no animals can be harmed in the spectacle. No money should be wasted. And the environment should not be damaged. A global launch, something of the magnitude of Tegra K1, and of course no budget and no one can be harmed. It's an impossible task. And what they came up with was this crop circle. Now this is a field of barley. It turns out barley is between cash crops and it'll just be plowed over. So there's no food was harmed. And because barley is pretty inexpensive, no money was wasted. Now what was interesting is this. This is in a small town south of Salinas in California. And when I learned about it, I saw it on CNN. I saw in headline news CNN. People thought aliens had done this. And the coverage has been fantastic. Canada to the south, Brazil and Mexico, all the way to the west, Thailand and China, and to the east, UK, of course, where all the crop circles start. Aliens go to. And the coverage has been fantastic. The coverage has been fantastic. These are a couple of our favorites. Somebody wanted to throw a New Year's party. If you could read that, it says, crop circle in Chular, California. Chular, California, by the way, has 1,100 citizens. They have since been visited by fleets of helicopters from news stations. Hundreds of people have pulled off the side of the road to take a look at this astronomical phenomenon. And this one's fantastic. It says, guys, they're going to have a party on New Year's Eve. Guys are $20. Ladies get in for free. And drinks are special, DJ dance floor, and something called Bongzilla. And so this is on that guy's website. The one on the right is really fantastic. I really love this. She's a reporter, and she decoded it. She looked at this and she's figured it out. She figured out that in fact it's Braille. She figured out that that is Braille, and she's reporting this on the news. That this phenomenon is in fact in Braille, and the code that she broke is 192. 192 repeated. 192 repeated. Well, of course it's 192 because the marketing team was very clever. Haha. Tegra K1, 192 cores. And this reporter should be given an award. She could be a cryptologist, and she discovered that this is 192. She thought it was actually an internet address. But anyways, fantastic job from the marketing team. So you have the heart of GeForce, you have the soul of Tesla, and you have the spirit of Nvidia marketing at work. So give those guys a round of applause. And there you have it. This is our announcement today. We talked about three things: games, chips, and cars, as we continue to advance the visual computing revolution. The first part about games, we talked about game streaming, that is making possible extending the PC experience. We talked about G-Sync, this revolutionary new monitor that makes it possible for you to enjoy computer graphics in a non-stutter, without lag. We talked about Tegra K1, the heart of GeForce, the soul of Tesla, the world's first 192-core super chip. It comes in two versions, 32-bit quad-core, 64-bit dual Denver. Look forward to telling you more about Denver in the coming months. And then we talked about Tegra K1 VCM, a vehicle computing module, putting a supercomputer in your car. Your car is going to be one of the areas, one of the computing platforms that's going to go through dramatic revolution over the next several years. Really, really exciting change, led by some of the world's best engineers. Some of them are right here in the audience today. You're going to have a supercomputer in your car. It's going to make it possible for your car to eventually lead to semi-autonomous driving. And also, we believe that computer graphics should end at industrial design. It should extend all the way into your real-time digital infotainment systems and digital clusters. I want to thank all of you for joining us today. Have a happy new year and have a great CES. Thank you.